Today, we will discuss extreme gradient boosting, commonly known as XGBoost. XGBoost is one of the most powerful and widely used machine learning algorithms for both regression and classification problems. It has gained popularity because of its exceptional predictive performance, computational efficiency, and ability to handle complex and nonlinear behavior of the data. XGBoost has been successfully applied in many fields, including engineering, healthcare, finance, and many other science competitions. Many machine learning algorithms perform well, but XGBoost is specifically designed to improve accuracy while maintaining computational efficiency. It often outperforms traditional models because it learns from previous mistakes and continuously improves predictions. This makes it particularly effective for complex engineering datasets where multiple variables interact in nonlinear ways. XGBoost is an ensemble learning algorithm based on gradient boosting. Instead of building many independent trees like random forest, XGBoost builds trees sequentially. Each new tree focuses on correcting the errors made by the previous trees. Through this iterative process, the model gradually becomes more accurate. The process begins with an initial tree that generates a prediction. Naturally, that prediction contains some error. Instead of ignoring those mistakes and errors, XGBoost tries to calculate the residuals or prediction errors and trains a second tree specifically to correct those mistakes. Additional trees continue learning from the remaining errors, gradually improving the performance of the model. As we move down the sequence of trees shown in the figure, the residuals become smaller and the predictions become more accurate. Eventually, the combined output of all these trees produces a highly accurate final prediction. This ability to continuously learn from mistakes is what makes XGBoost particularly effective for complex engineering problems involving nonlinear in relationships and interacting variables. One of the easiest ways to understand XGBoost is through this student learning analogy. Imagine a student taking a series of exams. On the first exam, the student scores 70. After reviewing mistakes and learning from them, their score improves to 82 on the second exam. With additional learning and correction of remaining weaknesses, the score increases to 92 on the third exam. XGBoost follows a very similar process. The first tree generates an initial prediction, which may contain some significant errors. The next tree focuses on learning those errors, known as residuals, and improves the prediction. Additional trees continue correcting the remaining mistakes or remaining errors until the prediction becomes increasingly accurate. Rather than building independent trees, each tree builds upon the knowledge gained from previous tree. This step-by-step improvement is what makes XGBoost such a powerful predictive model. The XGBoost process begins with an initial prediction. The model then calculates the prediction errors and builds a new tree specifically designed to reduce those errors. This process repeats over multiple boosting runs. Each new tree focuses on correcting the remaining mistakes, gradually improving the performance or the accuracy of the model. The final prediction is obtained by combining the contributions of all the trees in the ensemble. To understand XGBoost, we first need to understand the concept of residual. A residual is simply the difference between the actual value and the model's prediction. In other words, it represents the prediction error. In the example shown, the actual TSR value or the actual tensile strength ratio value is 90, while the model predicts 80. So the residual is just the difference, which is 10. This residual tells us how much the model missed the target. Unlike many machine learning algorithms that focus directly on predicting the target value, XGBoost focuses on learning these residuals. After the first tree makes a prediction, the next tree is trained to predict the remaining error. If some error still remains, another tree is added to learn that error as well. As shown on the right, tree 1 produces the initial prediction. Tree 2 learns the residual error, and tree 3 further refines the prediction. By repeatedly reducing residuals, the model gradually moves closer to actual value and becomes more accurate. The term gradient boosting originates from the optimization process used to reduce prediction errors. The loss function shown on the left measures the difference between actual values and predicted values. The objective is to minimize this error as much as possible. The concept can be visualized as a ball rolling downhill toward the lowest point of a landscape. The gradient indicates the direction of steepest ascent, so moving in the opposite direction helps the model reduce error most efficiently. Rather than attempting to solve the entire problem at once, XGBoost makes a series of small improvements. The diagram on the right illustrates this process. The first tree generates an initial prediction. The model then calculates the residual error and uses gradient information to build a second tree that focuses specifically on correcting those mistakes. Additional trees continue refining the prediction until the overall loss becomes very small. This sequential error correction process is the foundation of gradient boosting. Several innovations make XGBoost more powerful than traditional gradient boosting models. These enhancements improve accuracy, computational efficiency, and model robustness. One important feature is regularization, which penalizes overly complex models and helps prevent overfitting. Another feature is shrinkage or learning rate control, which allows the model to make small and controlled improvements rather than large adjustments that could lead to unstable learning. XGBoost also uses tree pruning to remove branches that contribute little to prediction accuracy, creating simpler and more efficient models. In addition, the algorithm supports parallel computation, allowing many calculations to occur simultaneously and significantly reducing training time. Finally, XGBoost can automatically handle missing values by learning the optimal paths for incomplete observations. Together, these enhancements explain why XGBoost achieves higher accuracy and faster training than many competing machine learning algorithms. Consider a pavement engineering problem where the goal is to predict the tensile strength ratio of an asphalt mixture. The model receives several input variables including binder content, air voids content, voids in mineral aggregate, voids filled with asphalt, wrap content, nominal maximum aggregate size, and probably some other mixture characteristics. Rather than relying on a single decision tree, XGBoost builds a sequence of boosted trees. Each tree learns from the errors of the previous trees and contributes a small correction to the final prediction. Let's see how XGBoost performs a classification task using an asphalt mixture example. The objective is to determine whether a mixture has a low or high moisture susceptibility or high risk of moisture damage. The process begins with the input variables shown on the left, including air void content, the VMA, VFA, asphalt content, wrap content, and probably some other mixture characteristics. These variables are provided to the XGBoost model. Unlike random forest, which builds trees independently and combines their votes, XGBoost builds trees sequentially. The first tree generates an initial prediction, which in this example classifies the mixture as failed. The model then calculates the residual errors and builds a second tree specifically to reduce those errors. Additional trees continue learning from the remaining mistakes and gradually improve the prediction. As the boosting process continues, the prediction score is updated by adding contribution from each new tree. The final score is then converted into a probability using a sigmoid function. If the probability exceeds a threshold, typically 0.5, the mixture is classified as pass, otherwise it is classified as failed. In this example, the probability gradually increases from 0.23 to 0.62 as additional trees correct the residual errors. As a result, the final prediction changes from fail to pass, indicating a low risk of moisture damage. This example highlights the key strengths of XGBoost, where a classification can change as the model tries to correct itself. One advantage of XGBoost is that it not only generates predictions but also helps identify which variables are most influential in the prediction process. The feature importance chart ranks the input variables according to their contribution to reducing prediction error. Variables appearing near the top of the chart have the greatest influence on model performance, while those near the bottom contribute less. In this example, air voids appear to be the most important predictor, followed by binder content and wrap content. This indicates that changes in these variables have a strong impact on the predicted performance or have a strong impact on the tensile strength ratio. Feature importance analysis provides valuable engineering insight because it helps researchers and engineers understand the underlying drivers of system behavior rather than treating the model as a complete black box. Developing a model is only part of the process. We must also evaluate how well it performs on unseen data. Several performance metrics are commonly used for this purpose. The R-squared value indicates how much of the variability in the target variable is explained by the model. Values closer to 1 indicate better predictive capability. The mean absolute error represents the average magnitude of prediction errors and is often easy to interpret because it uses the same units as the target variable. The root mean square error is similar but places greater emphasis on larger errors. This makes APSE particularly useful when large prediction errors are undesirable. Together, these error metrics provide a comprehensive assessment of model accuracy and reliability. The predictive capability of XGBoost depends on several hyperparameters that control how the model learns from data. The number of trees determines how many boosting runs are performed. The learning rate controls the contribution of each tree to the final prediction. Smaller learning rates generally improve generalization but require more trees. The maximum tree depth controls model complexity. Deeper trees can capture more intricate relationships but may increase the risk of overfitting. Additional parameters such as subsampling and column sampling introduce randomness into the learning and improve generalization. Selecting appropriate hyperparameter values is often one of the most important steps in developing a high-performing XGBoost model. XGBoost has become one of the most successful machine learning algorithms because it combines several desirable characteristics in a single framework. It is capable of modeling highly nonlinear relationships, handling complex interactions among variables, and delivering excellent predictive accuracy. The algorithm is computationally efficient and scales well to large datasets. Built-in regularization improves robustness and helps prevent overfitting, while automatic handling of missing values reduces preprocessing requirements. XGBoost is not a perfect solution for every problem. One challenge is the relatively large number of hyperparameters that must be selected and tuned. The model can also become computationally demanding when extensive hyperparameter optimization is performed. In addition, because predictions are generated by many boosted theories working together, interpreting individual predictions can be difficult. Another concern is overfitting. Although XGBoost includes regularization mechanisms, improper parameter settings can still lead to models that perform exceptionally well on training data but poorly on new observations. This slide demonstrates how easy it is to implement XGBoost in Python. The code begins by importing the XGB regressor class from the XGBoost library. Several hyperparameters are then specified, including the number of trees, learning rate, maximum tree depth, and random seed. The model is trained using the fit function with the training dataset. Once training is complete, predictions are generated using the predict function. The workflow diagram on the right summarizes the typical machine learning process. First, data are loaded and prepared. Next, the XGBoost is trained. Then predictions are generated, and finally the model is evaluated using appropriate performance metrics. Although both XGBoost and random forest are tree-based ensemble learning methods, they differ in how they build trees. Random forest builds many trees independently and combines their predictions through averaging or voting. In contrast, XGBoost builds trees sequentially, with each new tree focusing on correcting the errors from the previous trees. Random forest is generally easier to tune and less sensitive to hyperparameter settings, while XGBoost often achieves higher predictive accuracy, especially on complex datasets. However, XGBoost typically requires more parameter tuning and computational effort. In summary, XGBoost is a powerful ensemble tree-based learning algorithm that builds decision trees sequentially, with each tree correcting the errors of previous trees. It's a combination of boosting, regularization, and efficient computation allows it to achieve high predictive accuracy while maintaining good generalization. As we have seen, XGBoost can be applied to both regression and classification problems and is widely used in engineering applications involving complex and nonlinear datasets.